Okay, so let me introduce the second speaker of today. This is Eilind Karlsson from TU Munich, and she's going to talk about dualizability in higher Morita categories.
Okay, so thank you for the introduction, and thank you for letting me speak, and also thank you for organizing this workshop. So I really appreciate kind of the mix of people that you gathered together. I think it's very cool. Yeah, I guess I should get started. So I want to say, first of all, if you don't know any of the words that appear in my title, you should be fine. I will really do like a down-to-earth introduction, and hopefully you can all follow that. So just like a brief outline of what I will talk about today. So I'll split it into 3 parts. And the 2 first ones are like the basics we need. So first of all, I'll talk a little bit about topological field theories. So again, the ones that were in Luca's talk probably will then hear it twice, but I don't think it hurts. So I'll do first the ordinary version, a little bit about that, and then I'll talk about what so-called fully extended TFTs are. So that's different from what we've seen earlier today. And then I'll mention the cobordism hypothesis. It's kind of very crucial for what I'm doing, a very strong statement. And then I'll spend a bit of time on my second part, which is about dualizability. So what it means for an object to be dualizable in these higher categories that appear. I'll try to connect it to kind of the bordisms that you have already seen in my first part. And then towards the end, I'll get to the fun stuff, at least for me. So I'll plug in a specific target for the TFTs I'm considering. And that will be the so-called higher Morita category, which is denoted by Alch n of S. And I'll flip it around a little bit from what I usually do. I'll start talking about what n+1 dualizability in here should correspond to. And then I'll give you a very brief kind of flavors of what factorization homology is. So that's something that appears when you want to talk about n+1 dualizability. And then if I have time, I think I'll give you a brief sketch of how AlGen is constructed. So there's 2 different versions. They have slightly different flavors to them, and I'll just sketch them out. Okay, so, and also, so I don't mind taking questions at any point during my talk, and I guess you're not allowed to actually speak, but feel free to write in the chat, and maybe Karina can forward the questions if anything is unclear. Okay.
Yes, or you can also just raise your hand and I'll unmute.
Right, then it will be visible.
Yes.
So feel free to ask at any point if something is unclear or you want some more details. So let's start. What are fully extended TFTs? And to get there, we kind of need just the first definition of a TFT. So a topological field theory, like you just saw, it will be a symmetric monoidal functor, often denoted by this curly C. And the crucial part is that it's out of some bordism category. Here, just for the sake of the example, I have orientations, but you can have different structures on your bordisms. And then the low dimensional target is typically the category of vector spaces, but here you can plug in, like you already saw in Luca's talk, like any symmetric monoidal category. So just for sake of being coherent or have everything in this talk, the objects in this bordism category will be closed oriented d-1 dimensional manifolds. And your one morphisms, if I want this to be an ordinary category, I'll take diffeomorphism classes of d-dimensional cobordisms. And then, like Lucas said, and we'll see for the fully extended case, there are different ways of making this into a higher category, but now just think of it as a normal category. And our composition is by gluing these bordisms together, and it's symmetric monoidal by the disjoint union. So you already saw that kind of two-dimensional TFTs, they correspond to certain Frobenius algebras. And I want to do an even simpler example. So I want to look at the one-dimensional case, so proper baby case, but it will be useful for later. So if I plug in d equals 1 here, my objects will be oriented zero-dimensional manifolds, so essentially just disjoint union of points, and here they come with two orientations. So I'll just, and yeah, so I've drawn out just one point with positive orientation and one point with negative orientation. And to construct a functor, I need to say what I assign to these. So I choose to assign some vector space to my positively oriented point. And just for the sake of saving some time, I already know the answer, and I will tell you that to the negatively oriented point, what you want to assign is the dual vector space. A priori, you don't know this, but just for the sake of saving time. Now, some of the one morphisms that appear will look like this. So the first one here will be just the identity on a positively oriented point. So it will just map to the identity morphism on V. Now, this cap, you should read as a bordism from the like two copies of a point with opposite orientation into the empty set. So this will correspond briefly to an evaluation of your vector space. So from V tensor V dual into the underlying field, whereas this cap will correspond to the co-evaluation. So I mean, it will, I'm telling you it will, and I'll show you why. So, and the reason I call these maps evaluation and co-evaluation is because we have a certain relationship in between certain cobordisms. So here, so these are typically called like snake relations or triangle identities or sorrow moves in different incarnations. But what you should read this as is we have two one morphisms, and then we compose them with these two one morphisms. And if you just kind of pull the strings apart, this is diffeomorphic to just the identity on the positively oriented point. And if I write this out in terms of the evaluation and co-evaluation that I had on the other side, this is the relation I got. So I said to the line, I will just send it to the identity of my underlying or my vector space. And here we should read it. So here we have identity tensor co-evaluation, which is exactly identity tensor co-evaluation coming from these, and then composed with evaluation tensor identity. And this is exactly what you ask for having a dual of a vector space for these kind of compositions to be equal to identity. And also there's an opposite one where you kind of compose the cap and the cup in the opposite order. I just haven't drawn it out. So, okay, if you're seeing this for the first time, then takeaway is, so now to have this co-evaluation, actually, like for co-evaluation to exist here, you need your vector space to be finite dimensional. So the takeaway is that I will get a TFT if and only if I assign to my positively oriented point not just any vector field, but a finite dimensional one. But given that V is finite dimensional, then that is already enough to have a well-defined symmetric monoidal functor C. So like the baby case we get is that one-dimensional TFTs are the same here with target and vector spaces are the same as finite dimensional vector spaces. And just for the sake of making or writing it in an analogous way to what you will see later, these are the one dualizable objects in the category of vector spaces. And now maybe the physicists among you will be a little bit skeptical. So asking for V to be finite dimensional is very strong, and it's too strong for most physical situations. And I mean, for the sake of this, like, think of it as a toy example. So don't be too disheartened about it. Okay. So that was the basic part, and now let's talk about what a fully extended TFT is, or a local one. So it will again be a symmetric monoidal functor. But now in the appropriate sense, because we will have to work with higher categories. So it's again denoted typically by some curly C, and it's out of a higher category of framed Bourdisms. So I'll talk about fully extended framed TFTs here, and we plug in some suitable symmetric monoidal higher target category. And okay, so I want to start with explaining roughly how you can kind of put some pictures onto what this category should be. This is a very like informal thing, but at least I find it useful to have something concrete to picture. So objects are again just zero manifolds, some finite disjoint union of zero manifolds. They will come with a framing, and I will completely suppress that because I don't think it helps if you're seeing it for the first time, but just have at the back of your mind that there's something additional to these points. And now we have one morphisms, which you can think of as being Bourdisms between objects. And I'll tell you in a moment how to read these. So my convention is to read them from left to right. So as we already saw, like this should be from 2 points to the empty set, and then empty set to 2 points. Here we have the identity. You can of course also send something to the circle. But now, since I'm saying we want a higher category, we need to continue having higher morphisms. So for 2 morphisms, these are kind of some examples of what you can picture. So read them bottom to top, and these will be kind of Bourdisms between Bourdisms. Between objects. So what appears are manifolds with corners. So again, like we will, for example, have the pair of pens that you already saw in Luca's talk for 2-dimensional TFTs. So this one is a morphism from 2 copies of the circle into 1 copy of the circle. But we can also have things like this saddle. So this one you should read as going from 2 copies of the identity on a point into this cup and cap after each other. So we have a lot more than what you would expect from a 2-dimensional TFT, for example. And then this pattern continues. I'm not going to try to draw high-dimensional manifolds. This is already pushing my drawing skills. And then somehow the takeaway is that this continues up to dimension D for Bourd D. So we have D morphisms are D-dimensional Bourdisms. And then they change their nature. So we wanted, like Lucas talked about, how you can think of the Bourdism category as an infinity 1 category, kind of encoding how things are diffeomorphic. That's exactly what we want to do here as well, just as an infinity D category. So the higher morphisms, like D+1 morphisms, will be diffeomorphisms of D-dimensional Bourdisms. And here all of the morphisms will then be invertible somehow, what this infinity D part tries to capture. And then, I'm sorry, And then you can take isotopies of diffeomorphisms and so on and so forth. And that's how we kind of continue this pattern. Okay, so if you've never seen a higher category, I hope this made for kind of a slightly simple first picture of them. And now I want to explain why they're called fully extended. So, and also why they're useful. So at least in theory, we can think of fully extended TFTs as making things computable. So in a two-dimensional TFT, for example, like an ordinary two-dimensional TFT, we have a pair of pens, but there's nothing more we can do about it. Like we can't chop it up. We need to know what to assign to this surface. But here, since we know what to do even on manifolds with corners and like all the way down to the point, we can kind of chop it up even more. And essentially all of the pieces that are here will be like disks. So, and the reason they're called fully extended is that to be able to do that, we need to know what to do with the point. So a two-dimensional ordinary TFT would kind of correspond to these and more pieces that will look similar, like you just saw in Luca's talk. And being able to extend it down means, okay, I need to have a compatible way of assigning something to a point, like going all the way down to zero-dimensional things in a compatible way. And at least in theory, that will make things computable. So I mean, of course, 2 is a very baby example, but as you work with higher dimensional manifolds or higher dimensional like ordinary TFTs, it becomes increasingly hard to know what to do. And so this is, at least in spirit, should make things easier. Okay, and now, so that's the reason why they're called or named fully extended, but another name for them are local TFTs. And this is due to the cobordism hypothesis. So if you're a physicist in the audience, you should really think of this as a locality statement. And I'll say again why after I've said the statement itself. So it goes as follows. So a d-dimensional fully extended frame TFT, meaning a functor that's symmetric monoidal in here. So that's why the tensor product is there. So from this framed higher Bordism category into some target, this is equivalent to what's called de-dualizable objects in your target. And so this is in a similar spirit to what I showed on the first slide, that one-dimensional TFTs are simply given by one dualizable objects in vector spaces. And now we have a way of generalizing this. And the assignment goes in the same way. So this is essentially given by evaluating your TFT, so your functor here, on a point with a certain framing. So which is then the reason why you can think of this as being a locality statement. Essentially, if you have a good assignment of your TFT to a point, then everything else will follow. Then your TFT is well defined and you know what to do on all the other pieces. And the nice thing about this statement, at least for me personally, is that the left-hand side can be very tricky to work with. Defining one of these functors is essentially, there are many things you need to check and there are many things you need to assign, whereas this is a purely categorical notion. You can give it to like any mathematician that's working on higher categories and not talk about TFTs. And you can say like, hey, I have this category. What are the de-dualizable objects in there? Okay, and so at least in certain cases, it can be easier to work on the right-hand side instead of defining a TFT. Okay, and I should mention some names. So originally, I think it was Baz and Dolan that conjectured this, and then in 2 dimensions, it's due to Shomaprisen Ostrogowski, might butcher his name. And then Lurie has an extended sketch of proof, and there's a different approach to the proof by Ella Francis, and then there's probably like a long list of names I should also add, but they're now in ... Okay, and just as a brief outline, so what I will do, or what I'm working on, is plugging in a specific target. So I'm plugging in for C to be my like this higher Morita category, and I'm looking at n+1 dualizability in algen. That's somehow what we're getting at when we're done with the basics. Okay, are there any questions at this point? And I'll give you at least a 15-second to think about it. I also hate awkward silences, so it won't be more than, yeah. You can someone unmute Luke? He's raising his hand. I don't know what happened.
I was like muted twice or something and it canceled each other. I don't know. I wanted to ask, is S a one category, symmetric monoidal one category, or already a higher category?
So you can plug in an infinity K category in S, plus ask for it to have certain properties. So it has to be nice in a certain way, which, I mean, we can talk about later. I probably won't mention the technical conditions for this to actually exist. But yeah, you can plug in infinity K. Okay,
but here you don't.
So no, for what I'm doing, it's enough with infinity 1.
Okay, thanks.
Yeah, good question. Okay, so
there's also a question in the chat, but probably you will get there, because the question is, could you please say more what dedualizability is?
Yeah, so that's the next slide.
Okay.
So take a moment. I thought that would be part 2. So that's what somewhere here under the slides. So part 2, what is dualizability? And I'll not give the full kind of higher categorical definitions, but I'll sketch out what it means in the Bordism category and then translate it, at least lower dimensional cases, to C. So for an object to be one dualizable, it's essentially what we have already seen. So here is my object. I need kind of a dual object, which will be a point, and the framing will be different, which is why I've given it a cross. And if you want to know more, I'm happy to discuss it maybe in the gather town later. And then certain one morphisms, which look exactly like what we had on the first slide. And this, if you want to translate it to your target higher category, right here, just ordinary category as well, this amounts to asking for a dual object and evaluation and co-evaluation one morphisms, such that you have a relationship between them, look like the snake relation. So now, like the new part is then, if I want to do two dualizable, I need 2 additional one morphisms. And even though these look the same, they're not. So again, there's something kind of happening with the framing. So just kind of look at the colors and think that they're different. So these will somehow come together, and these depend on each other. And then I need some 2 morphisms. So they will look like the saddle and kind of a cup and a cap. Yeah, so you should read this again, like from the composition of these guys into the identity, and then here you go from the identity on just the underlying monoidal unit, which is the empty set, into the other way you can compose these two. And then similarly for this pair. And if I want to say what this means in C, then I'm asking exactly for left adjoint one morphisms of the evaluation and the co-evaluation that appeared. So you see here the order is kind of swapped, which correspond to so the left adjoint of the evaluation will be this guy, kind of correspond to this guy. So it goes from here the empty set into C tensor C dual, or object and the dual object. So here in C tensor C dual, and then this will correspond to this guy, and the corresponding unit and co-unit 2 morphisms, which again, so I shared my slides, and maybe it makes more sense to actually just sit down and stare at it for a couple of minutes, but it's essentially the same pattern. So here you have evaluation left adjoint into identity on these 2 objects. Again, here identity and trivial into the opposite way of composing them. So left adjoint and evaluation. And then certain compatibilities between those. And I should mention, so the reason the list on the right here is relatively short, and the reason I can say here I'm asking for left adjoint, I could also set just the right adjoint, either one is fine. It's due to result by Arajo. I maybe butcher also his name, I'm very sorry, but he was speaking on Tuesday morning, I think, on a different topic, and he showed that kind of providing this partial dualizability data is already enough. Yeah, and again, like the takeaway is that these are very algebraic conditions and can be easier to work with, at least. So I hope, and this is really the notion of an object being 1 or 2 dualizable, which is what's relevant for the cobordism hypothesis. But there's of course a way of talking about in a higher category just a k-morphism having an adjoint as well. Just very much simplified this slide. So I hope it gives you some feel at what you should check, what you should look at. And then, yeah, then maybe unless someone has a pressing question, I'll go to the third part. This wasn't that long. Okay, so let's start with talking about the target. And now essentially the slide's also answering what you were asking about, Luke. So I at least have it here. So this specific target, which is the higher Morita category, and here, so like we already discussed a little bit, you can plug in some nice infinity K category in general, but if you like to work with examples and infinity categories scare you, then think of plugging in like vector spaces or chain complexes or the category of categories. And then up to details, those are fine. And then in total, this algen will be an infinity n plus k category. Okay, so first of all, the one motivating example and the reason for this having the name that it has is the so-called Morita 2 category. And you can think of this as being alg1 of vector spaces. So it will be more clear once we get to like the full definition. But either way, so the objects in here are just associative algebras. Some A and B and so on. And my 1 morphisms, you might already guess if you don't know, they will be bimodules. So for M and AB bimodule, you should read this as a 1 morphism from A to B. And then the 2 morphisms are, or the reasonable thing to take as 2 morphisms are just bimodule homomorphisms. Okay, so this is somehow the baby case, and it captures exactly like algebras up to Morita equivalence. So that's why it's the Morita 2 category. And then I just stated, okay. Some other examples of things that one might want to generalize into such a higher Morita category And these will be examples of EN algebras. So I'll just give you the one sentence I thought I would say about this. So EN algebras are algebras over the little disk operaad. You saw framed EN algebras appear in Luca's talk. And essentially, if you don't have this additional point, that's somehow what you have is the ordinary little disk operaad. But if you don't know it, then let's go to the examples, pick your favorite one and stick to that one for the rest of the talk. So if you look at S being the category of vector spaces, an E1 algebra in vector spaces will be exactly an associative algebra. So what we have here, an E2 algebra will be a commutative algebra. If you look instead at the category of categories, an E1 algebra will be a tensor category. An E2 algebra will be a braided tensor category. So somehow you see this is a 2 category, this is a 1 category. So that's somehow the reason for this braid. So if I would say n equals 3, you would get symmetric braided tensor category of categories. Okay, and then, so that's one gadget that's used to write down these Morita categories. And the second one I'm more familiar with are so-called locally constant factorization algebras, which you can think of as certain precaucheves. And if we have time, we'll talk a little bit about them, but I think, yeah, just so EN algebras and locally constant factorization algebras and Rn are equivalent. So you can also, for this, pick one of your favorite in the list of examples if you're not familiar with them. And maybe the things I would say, since this is more of a physicsy audience, is that factorization algebras in general, so without locally constant, they can be seen as one way of encoding observables in a QFT, and they will roughly correspond to what you would look at for perturbative QFTs. I hope we will see more about this afternoon. That's at least what I think. And then roughly taking the locally constant ones should be then the observables of a TFT. So when things are, I don't need to say more about factorization algebras for that, but yes, that's roughly kind of the thing that would make sense for a TFT. And one instance where they show up is perturbative Chern-Simons theory. So just to give you some motivation if you come more from a physicsy background. Okay, and now I'm finally at a place where I can say kind of what I am currently working on. So this is still work in progress, and it's a statement about an E2 algebra. So an object in this Morita 2 category being 3 dualizable. So it goes as follows: an E2 algebra A is 3 dualizable if and only if A has an adjoint as the module of the factorization homologies. And now you might be scared because factorization homology is a new word here. I think we'll also see more of that today, but very roughly, it's a homology theory for framed n manifolds that takes coefficients in EN algebras. And I'll give you some baby examples on the next slide. Don't worry too much. And the condition itself is the following. So this denotes factorization homology with coefficients in my E2 algebra over a certain manifolds, depending on K. Okay, and I'll show you a picture for one of these cases once I've talked a little bit more about factorization homology. But yeah, so should mention, so it's a theorem by Lurie. A similar pattern for this if you look at 2 dualizability in ALGE1. And it's also shown by Bouchier, Jordan, and Snyder for plugging in S being the category of categories in this incarnation, so in E2 algebra in ALGE2 of cat. And it's also, so just as an outlook, this is a conjecture for even higher n, so by Lurie. So we do expect that an E in algebra is n+1 dualizable if and only if it is adjoints for these factorization homologies. Okay, but I'll let you stare at that for a tiny second. I see a lot of staring, that's good. So just a tiny, very tiny introduction or some flavors of what factorization homology does. So the definition, if it's helpful, and if it's not, then just disregard it. So in E in algebra, we saw Lucas' talk as kind of, you attach something to disks. So you can see it as a functor from a category of frame disks into S. And now factorization homology is, so you can also include these frame disks into category of manifolds. And factorization homology is the left con extension of A along this inclusion. So it's typically then denoted the coefficients in A over some manifold that goes in here. I mean, if these are all words you don't know, then just disregard it. And I'll give you some baby cases. But first of all, so the one takeaway that I want you to have from this slide is that the framing of your manifold is really the important thing when you want to look at factorization homology. So you really kind of, you can have the same manifold with different framings and they will give different results if you look at the factorization homology of that. And the very basic example, so you can look at, if we take, this was one of the examples, and E1 algebra in vector spaces, so in associative algebra, then 2 to R1 with just the standard framing, so it's just indicated by this arrow, we will attach A. That's what factorization homology does for us. But now, if we look at instead R1 with the opposite framing, we will instead have to attach the opposite algebra. And yeah, you will just have to believe me, but really here we have the same manifold and the framing changes and we attach something different. And another example, just to kind of have some cool mathematical structures appear, is if we look at, again, what factorization homology would assign to S1. Picture it like this, and I have kind of a counterclockwise framing in this, then we have an excision property. So this is an homology theory. We expect to have some notion of excision. So we can look at our S1 as being 2 copies of R. I'm almost drawing in something that will appear later. I'll draw it into the figure in a second, over. So kind of, we chop it up in this way, at +1, yeah, -1. And then I have 2 copies of R, so one will kind of extend past, call it this one, the other one like this-ish. And then they're glued over +1, -1 across another copy of R. And now essentially everything we have are copies of R, and we know what to do with those. And the only tricky part is that for this -1 cross R, that will correspond to the framing being the opposite direction. So in total, we have so this would kind of be the excision property, some relative tensor product, +1, -1. And this is why I pre-write a lot of things, because my handwriting is not amazing. So to the 2 copies of R, like the blue and the purple, we assign A. And then here as well A, but this one will correspond, like the -1 will give us opposite orientation. And this is exactly the Serre-Hochschild homology if we would have taken a slightly more refined target. So for example, DG vector spaces, we would actually get the whole Hochschild complex. I mean, if you've seen these words before, then maybe that's already a good motivation why this is a cool gadget to pick out interesting algebraic structures. And now let me kind of sketch out what one of these conditions in the above theorem is. So, okay, see if I can. Okay, so this is essentially what the theorem will give for k equals 2. So I'll write it here and we can copy it down. So it will be factorization homology for k equals 2, then I will have over S1 cross 1 copy of R, the coefficients in A, and then the framings are important. And here I get the framing from the K disk. So that's exactly what I've been, oh, I'm sorry, I don't know what happened. That's what I have been drawing in here. So imagine you would fill in here and just have the standard kind of Blackboard framing. That's what you see. Okay, and if I draw it like this, it seems like a very random thing to appear, but let's look a little bit at what it could be. So first of all, the statement goes, I want A to be, to have an adjoint as a module over this factorization homology. So for this to make sense, I need to understand how A is a module of this factorization homology. But this is essentially, so this is the picture you should look at now. And the disk here is equivalent to R2. So factorization homology would just attach A to this disk. And now saying that, okay, I want this annulus to be, or I want A to be a module of this, whatever we attach to this annulus, corresponds to just how you can stack annuli onto the disk. So here I hope you kind of can add in, if I stack the 2 annuli and then add it to the disk, or do one after the other, that will essentially be the same. This gives A this module structure over these factorization homologies. And then, okay, so that's somehow like this, this right-hand side is what appears in this theorem. And I kind of have to believe me that the picture I've drawn on the left-hand side is something that shows up if you're looking at this factorization algebra version of the Heyer-Morita category. So there is already a known statement about n-dualizability. And if you kind of spell that out, you will look at 2 morphisms that look essentially like this. And if you have the time to stare at these pictures later, you should be able to see that, okay, if I kind of picture taking this part of the disk and dragging it behind, and then also rotating 90 degrees counterclockwise, these are exactly the same. So I've stared at a lot of them, trust me, it's true, but it's also like a fun mental kind of gymnastics to do. Okay, so the takeaway is these are the things that appear in this theorem, and these are the things that appear if you're working explicitly in the Morita category. Okay, and then I don't know, Karina, do you want to tell me like how long can I go on?
Yeah, maybe you should try to wrap it up. Say like 2 more minutes. Okay,
so then I'm gonna just erase most of the things to show this slide, and then if you have questions, then ask me later. So this is just a rough outline of what the Heyer-Morita category is. So I'll sketch it out for n equals 2, and so there's one operatic version due to Rune Haugseng, and then there's one factorization algebra version due to Scheinbauer and Kalak, and then also Johnson-Fried and Steinbauer. Okay, and as objects, you should have guessed we take, I mean, here E2 algebras in general would be EN algebras in our underlying category, or locally constant factorization algebras on R2, essentially. And then as one morphisms, the pattern on the operatic side is to take like bimodules of E2 algebras, or in the factorization algebra world, something called constructible factorization algebra. So essentially, you kind of have something happening on this line. And so you come, like you have a stratification, here you have like a codimension 1 thing. And then for two morphisms, you will have bimodules of bimodules, or it's constructible for even codimension 2 things. And then you start adding in three morphisms or bimodule homomorphisms. So we take kind of morphisms of S that are compatible with the above. And if you want to instead of 2, say N, then just like this pattern continues for longer. So you'll have bimodules of bimodules of bimodules and so on. Or we start with something higher dimensional, so it takes us longer to get down to something like stratification where we have a point, very roughly. Yeah, and the known dualizability results for this is that every object will actually be undualizable. So that's what I used to get the picture we had above, like this one. Okay, and then I think I can actually say thank you for the attention. I think that was even less than 2 minutes. And yeah, feel free to ask questions. Yeah.
So thanks a lot for this very interesting talk. And yeah, questions. Okay, we have some. I think this time Pelle was first, so let me unmute you.
The important battle.
Yes.
Battle for the ages. Thank you for this this amazing talk. So this condition on sort of if I have something n-dualizable, I want to check that it's n+1 dualizable. Lurie tells us that like we should compute all these factorization homologies and then see if it's n-dualizable, or see it's dualizable over this thing. So somehow algebraically, like an EN algebra is essentially n commuting E1 algebra structures by
like
Dunn-Lurie additivity theorem, indeed. So, and should I view this factorization homology over Sk-1 times R something as like taking Hochschild homology in K-1 directions? And I'm sort of like, yeah, being dualizable as being sort of more dualizable as being dualizable in over sort of all the possible ways I can take Hochschild homology in a commuting way of this EN algebra object.
I think that's a very cool question. I've never tried thinking about it that way. I think I've had anyone phrase it that way.
I mean, this is what Sk-1 times, like if you do the factorization homology, take it over that product, it seems like you take like the Ek-1 Hochschild homology over these K preferred directions, and then you leave sort of the rest alone. That's what I noticed, and I thought like maybe this is like an algebraic way to express this.
I think it's a really cool question, but I have no idea if that kind of like works out thinking about it that way. So Lucas is saying that would be t to the power K-1 times. Yeah, so I think for
maybe I'm
S1 K-1.
Yeah. That's what I. So I mean, you do have to take the higher Hochschild homology and not Hochschild homology K times, but yeah, okay. People are complaining. Well, thanks anyway.
I don't think they're complaining. I mean, they said they had the same question, so.
I think we can also discuss about this then on GatherTown. I think that would be
that probably makes more sense for this one because I don't have a good answer like at the top of my head.
Thank you.
Okay, so then we have time for a second question. So that would be Nima.
Yeah, thank you very much for the great talk. I just have a short question. Well, depends, but so have you ever thought about using the Swiss cheese operator instead of the yen operator? Or?
No, I have not. And I mean, strictly speaking, I'm kind of happy about the fact that someone else constructed these higher Morita categories, and these are the two versions I know about, and I don't know if you would gain something by looking at the Swiss cheese operator and then trying to piece things together. So answer no. And what do you think? I mean, the counter question, what do you think it would like? Why should I try that in some sense?
Well, I mean,
what could I gain?
I'm not sure. I mean, it's just something that is interesting when you look at like higher defect stories, and this when you talk about like fully extended things and stuff.
Mm-hmm.
So I don't know. I thought that this might be something that.
Don't you just get like pairs of bi-modules, like you have like your little square, you have something in the middle, so you have a bi-module.
Yes.
But then on the outer side, you also put modules.
Yeah, I don't know. I thought that maybe there's something to say.
Yeah, no, fair question, but as far as I know, no, not in this setting.
Yeah, I mean, maybe you can go to the, yes. I mean, here, is this what you mean, Nima? That's like for the one morphisms? I mean, there you get like a Swiss cheese structure if, for example,
so you would also kind of add something here?
Yes, exactly. Like where you don't have something on the other side in some sense.
But I mean, I would just then call that, I mean, that might be, that was the wrong one. That might be very simplified, but I would just say that that's just the picture with like nothing filled in on one side. So, I mean, this is also a perfectly fine one morphism in my Morita category, right? So I could compose these together as long as the source and target are compatible, and then I would essentially have something like the picture you're talking about. I don't know if that will completely, like, I'm not super familiar with the Swiss cheese operator, just like briefly.
I mean, the Swiss cheese for me is always like something like, basically you have like these little discs with where you have boundary basically, right? So that's what it somehow mimics, like you have these semicircles instead of the circles, right?
Yeah.
So therefore, like, I don't know, I thought like if you know, if you don't have like two sides, like if you have like defect where you have like two sides, is something else than if you just mimic a boundary structure, you know, where there is basically nothing on the other side in some sense. But okay.
Yeah, so
yeah,
so
I think
short answer is at least no.
I mean, there are also some answers now in the chat. So I mean, Luke is basically saying what you just, the picture you've drawn. Yes, that's, I mean, yeah. That's you just
or
yeah, anyway, we can talk about this later.
Yeah. Okay. So then yeah, let us thank Eilind again and move the, and then we can just move the conversation to Gather Town.